Okay, well, let's go ahead and get on to surface area. Let's remind ourselves exactly what's going on in surface area. Now remember, when we're dealing with arc length, we're dealing with the fact that, you have something like this, and you're trying to get in, and remember that integration is a matter of accumulation, and you need to represent the cross-section, any cross-section, with respect to the variable, so that you can then accumulate or add up or sum up the infinite number of cross-sections with respect to that variable expression within the interval, the limits of integration. And what you get here is, you get this, and you make that, neat little triangle, and you zoom in far enough, and that gives you your arc length, right? But what's going to happen now is you're going to take the infinite number of arc lengths, the infinite number of infinitesimally thin arc lengths, and you're going to spin them around this axis, okay? So whereas when you were dealing with volumes of revolution, your cross sections were, disks. They were like coins, right? And you needed to find the volume of each one of the coins, and then you needed to use integration to stack them up and to add them all up over the over the interval. What we're doing here is we're not taking volumes, but we're taking sort of the outside area of a cylinder, right? And we're actually taking that and adding them all up. Well, here's the thing. Once you've done that, you recognize the fact that this length right here is your arc length, because it's not necessarily going to be flat. It's going to be a little bit off, right? And that's why we have that integral of dx dt squared plus dy dt squared dt. That takes into account the fact that it's excuse me, not going to be flat. It's going to be a little bit off, and it's that little bit off that you're going to be spinning around. But then, of course, you need the area. You need this, which is represented, this length right here is represented by the arc length. This long length right here was around the circle. So it's 2 pi r, right? So you have a rectangle here after you unfold it of arc length by 2 pi r. And 2 pi r is going to be 2 pi y if you're spinning it around the x-axis, because this right here is y. So that's how we transform the arc length expression right here, and we actually get the surface area in parametrics alpha to beta of 2 pi y dx dt squared plus dy dt squared dt. And that is the length times the width of these unfolded rectangles that I just spoke about. And this, of course, right here is the length, which, of course, is the circumference, right, 2 pi r. And this right here is the width of each of those, and that is the arc length, okay? So I'm just trying to get you to understand why the integral has the form that it has before we actually move on and start setting them up and trying to figure out exactly how to represent them as integrals, okay? And of course, this is related to the way that we did or have done surface area for functions, which went from a to b of 2 pi y 1 plus dy dx squared dx. And it was the same exact thing. This was my 2 pi r, which was my length because it was my circumference, and this right here was my arc length, which represented the width of those. It's just the fact that here we're integrating with respect to x, so it's a little bit simplified in the radicand. Here we're integrating with respect to t, so you just have to be careful about how you set up the radicand and how you set up the limits of integration. So let's go ahead and move on to our first example. Okay. Let's say we have x is equal to 1/4 t squared and y is equal to t plus 3. That's a set of parametrics and goes from 0 to 3 on t. Let's go ahead and take our x prime. Our x prime winds up being 1/2 t and our y prime winds up being 1. Well, that makes it actually rather easy. But here's the thing. I have to be told about which axis I'm going around because 2 pi r can be different. If I'm going around the x-axis, if I'm going around the x-axis, my 2 pi r is 2 pi y. If I'm going around the y-axis, it's 2 pi x, meaning I would use this expression instead of this one, okay? But this one is actually asking us to get the surface area going around the x-axis. It's always a little more customary. The y-axis is always a little more rare. So let's go ahead and go from 0 to 3, right? Those are my t values. 2 pi t plus 3. And then we just need x prime squared plus y prime squared dt. And this one actually can be actually done by hand if we wanted to, right? Because pull that 2 pi out in front from 0 to 3. T plus 3 be a little, it looks like it should be able to be done. It looks like it would take a little bit of finagling with respect to maybe some back substitution, but that should be it right about there, okay? Actually, that may take some other sort of substitution, but that looks like it should be able to be done. But neither here nor there right now. That is how I would set it up. I would solve it by hand if asked to solve it by hand, plop it into my calculator if I'm asked to evaluate it using my calculator, and that would be that. More important than proving our integration chops right there on that particular problem is understanding why this is set up the way that it is. Okay. Let's go ahead and do a trig example because we're never done until we've done a trig example. Theta plus sine theta, theta plus cosine theta are x and y respectively. Let's go ahead and run it from 0 to pi over 2. Now, x prime is going to be 1 plus cosine theta. Y prime is going to be 1 minus sine theta. And it should be very easy to set up, right? Surface area, you need your 2 pi r. Well, first of all, you need your limits of integration. If we're going around the x-axis, this right here is my r. So 2 pi r times the square root of x prime squared plus y prime squared. And then, since this one happens to be in terms of theta instead of t, it's d theta. And that would be how I would set it up. And it should be rather straightforward, okay? Now let's actually do one that requires us to change which way we're doing it as opposed to whether we're going around x or going around y. Actually, we could do this one. Let's go and do that. This is around the x-axis. The only thing that would be different if it was going around the y-axis, I would still have the same limits of integration because the limits of integration are with respect to t. The only difference would be here. It would be theta plus sine theta, 1 plus cosine theta squared plus 1 minus sine theta squared d theta. The only difference is that versus that, okay? This right here, what your book actually refers to as ds, okay, is the same for either one. And of course, 2 pi being a constant, 2 pi r, it's just your r that's different, okay? And this, of course, like I said, is going to be around the y-axis. So if it's around the x-axis, you get y for r. This is x expression is your r, okay? Well, let's go ahead and do, like I said, let's do one more. This one actually ought to be pretty easy. So we have 2t, y is equal to 3t. Well, that's kind of nice. Let's go from 0 to 3, okay? Now, obviously, x prime is 2, y prime is 3, and therefore if I want to go around the x-axis, I'm going to go, well, the surface area is going to be 0 to 3 of 2 pi y, and then it's just going to be 2 squared plus 3 squared dt. Well, that's 4 and 9, that's root 13. Root 13 and then 6 pi. So 6 pi times root 13 can be pulled out in front, and that is actually a pretty easy integral to figure out. Okay, if I was going around the y-axis, it would be very, very similar. I would just wind up with a little different constant out in front. It goes 0 to 3 of 2 pi, but I would have to put my x expression in here, and let's go ahead and just put that as root 13 since we already know what it is. So instead of 6 pi root 13, you would get 4 pi root 13 out in front t dt, and that is as well a very, very easy integral to actually figure out. You could plot that into your calculator and get going rather quickly. That brings us to the end of calculus of parametrics. I hope that that's clear in terms of the application for both derivatives and integrals. If it's not, please do shoot me an email and I'll try and shore that up. We're going to move on to 10.3 to 10.5 has to do with reintroduction into vectors and the introduction of vectors which have variables in them rather than just numbers, so what are called vector value functions. We'll get to that in a couple of videos, but that's something to look forward to. And from there we will then move on to polar and the application of calculus to polar equations here in just a little while, in a few videos time. But like I said, if you have any questions, shoot me an email and I'll just look forward to hearing from you. Bye-bye.